So we'll start. Okay, everybody. So we'll start today's seminar. We have our old friend from good old times in Warsaw, Konrad Aguilar, from Pomona College in California, and he will speak about the Bures metric and the quantum metric on the density space of a non-unital C-star.
Yeah. Okay. Well, thank you for the introduction, and thank you for the opportunity to speak. As Ray mentioned, this is a nice reunion from 10 years ago or something, almost. Yeah. I'm really enjoying the institute and the city. It's been really nice. Okay, so and thanks to I really like the setup, like the introduction talk before the pre-seminar, because this talk has both the unital case and the non-unital case. So I'm glad, thanks to Adar's talk and great job on the talk, I'll be able to kind of fast forward through the unital case so we can get to the non-unital case. Okay. All right, so let's first define the main object is a density space. Let's first talk about that. So it is a C-star algebra with the faithful trace. You can associate, so given that data, you can associate something called the density space, and this is a non-commutative analog to the space of probability density functions. So yes, in the commutative case with standard integration, well, any state is given by integration, but yeah, in that case, you do get the probability density functions with respect to that probability measure that you're given. The original setting for this, at least as far as I know, with the Bures metric, I haven't defined the metric yet, but was matrices and tau is the trace. In this case, you actually get the state space. So if you look at, so this stuff comes from quantum information theory and quantum computing, and these, if you look at the literature there, you have to be a little careful because sometimes they'll use density operators and the states interchangeably, because usually they are working with matrices, and then and then later I'll show you what this correspondence is if you haven't seen before. But anyway, this is a good way to think about this space itself, the density space. That's just states in the finite dimensional case. Now what about the Bures metric? So before I define it, I'll just give you like philosophically what it's doing. It's sort of doing something opposite of orthogonality, in the sense it's meant to highlight when things are orthogonal by giving it maximal distance. So there's this thing called the Bures metric, and what it does. So for example, in the matrix case, it being orthogonal, right? We don't need B star A because we have positive elements. But being orthogonal is equivalent to being maximal distance in the Bures metric. So its purpose is sort of to give this sort of, non like dual notion, I guess, to sort of orthogonality. At the expense of being a little informal. Okay, so a main motivation for working with the Bures metric is it provides certain contractivity of certain quantum channels. So quantum channels, again, in the literature, at least as far as I know, in the quantum computing, quantum information theory literature, they have different definitions all over the place. So just think about them as special CP maps, and sometimes they have CCP, UCP, or other conditions, but what they're interested in is contractivity with respect to the Bures metric. Well, contractivity with certain metrics, so then they get fixed points, which are steady states. So I will give you a fair warning that this is probably as far as my knowledge goes in the physics side of things. So I just wanted to, give you a warning that I may not know too much more than what's stated here. But now let's talk about the mathematics side a little bit more. So our work introduces, we have the Bures metric on this classic metric on the density space by Bures, generalized to C-star algebra, unital C-star algebra by Ferencz and Rahman. And what we're introducing today is a new metric on that. Well, this is a couple papers, a new metric on the density space, which we hope will provide further contractivity results. And we have some preliminary work here, but in the contractivity realm of things. We've also just been having fun just studying what this quantum metric looks like on the density space, how it compares to the Bures metric. Also looking at the Bures metric in the non-unital C-star algebra case, which hasn't been done before, and things like this. So we're not focusing on quantum channels in this talk, since we've been just focusing on sort of this, here's a new interesting metric space, and therefore topological space as well. That seems to be fun to play with. Yeah, I should mention before I move on, this was a project with several students and also collaborators. So that's why it came together from several projects with some students at Pomona College, as well as some collaborators as well, Katrina and Tron and a postdoc, Adam Yassine at Pomona College. So that's kind of why um, there's a lot. There's going to be a lot in this talk because it comes as like two projects formed into one. But it was fun. Okay, quantum metric spaces. I'll again probably go through this stuff and also some technical details later because again, Ara did a great job already introducing these things. But I had to use this quote from Riefel. So it's sort of a reminder that these things started because of this convergence of spaces. So I'll just read this quote. My interest in developing the theory of compact quantum metric spaces was stimulated by certain statements in the high energy physics string theory literature concerning non-commutative spaces that converge to other possibly non-commutative spaces. So although we're not even going to talk about these convergence of spaces in this talk. I like it as a reminder that like that was that was his interest and main interest in developing this theory. Anyway, again, I mentioned this non-commutative analog to Lipschitz functions, right? With the Lipschitz seminorm. So I'll fast forward through that. So now the idea that we're doing, introducing this idea of there's a way to actually embed the density space. So given a C-star algebra with the faithful trace that comes from a compact quantum metric space, well, that also is a compact quantum metric space with some seminorm L. You can actually construct an injective map into the state space. And as we saw in Artist's talk, this gives us a metric on the state space called the Monty-Djokovic metric. So the injective map into a metric space, you can always borrow a metric. This is the process of this new metric on the density space. Yeah. And I will also mention before we move on that we're going to work both with the unital case and non-unital case. How do you work with the non-unital case? You have to work with you can't work with compact quantum metric spaces, but thankfully in 2012, La Tremere introduced the notion of a quantum locate compact metric space, which allows us to do the same trick there to give us a new metric even in the non-unital case. But there are many different things that arise in that setting that we need to take care of because there's some nasty things that happen in the non-unital case. This is a situation where simply unitizing isn't enough. You have to actually do a lot more to get the right notion of a quantum metric space in the non-unital case. Okay, so now it's starting to formally define things. So again, we have the density space, positive elements of trace one given a faithful trace, and the Bures metric. So this is this thing that gives you this maximal distance in those cases. So let me say specifically what this meant before. I said maximal distance. The maximal distance here is one. Again, it's kind of arbitrary, but well, I mean, you're doing trace one, but yeah, it will make sense why that's one because you're doing trace one. But by maximal distance, informally, I meant distance one now in this space, in this distance. You can also look at the commutative case. So for example, with the Lebesgue measure, specifically the Lebesgue measure, this actually gives you that distance is, and in fact, with any state, this will actually work. You get distance is maximal distance if you're orthogonal, but in this case, that means, because you're dealing with positive functions, that means your support is disjoint. So again, just remind us, philosophically, this is the purpose of and concretely, this is the purpose of the Bures metric, is to give us sort of maximal distance from orthogonality. Yeah, so even in more abstract notions, that's how you should be thinking of this Bures metric. And again, this is introduced by Bures in 1969 in Ferencik and Rahman. And that was just in the case of like n by n matrices. And I believe also C to the n as well, just n copies of the complex numbers. But then Ferencik and Rahman extended this to unital C-star algebras. And then we've extended it to non-unital, which that case, again, is not that. It was basically Ferencik and Rahman that really brought it to the world of C-star algebras. Even though they didn't mention non-unital, the same definition works. It's only when you get to the quantum metric side where that's where things are getting. Yeah. Correct. Yeah, it's not. It's just it's convex. Yeah. Yeah. So that does cause issues later because you want to use some arguments that are for finite dimensional in the finite dimensional setting. So yeah, so you can't exactly use like vector space structures. But yeah. Okay, I wanted to mention this too. A funny thing happened. I gave a talk related to this stuff back in January 2026. And there was this professor there, Professor Kitty Craig, and it was at University of California, Santa Barbara, and it was in an applied math seminar, and which was exciting and fun to be able to talk with them about this. And she actually pointed out when I showed the commutative case, she was like, "That's actually the Hellinger distance from probability theory." And I had to look it up later what it was, but yeah, but it was nice that she pointed this out because I don't think like Bures, Fahrenheit and Rahama never mentioned the Hellinger. Neither does Bures, as far as I know, in other papers. So this was a nice new observation that it seems like Fahrenheit and Rahman accidentally didn't just generalize the Bures metric; they also generalized the Hellinger distance. So because that's the commutative case, so kind of a nice realization. So I'd like to give her credit for that because it sort of adds this layer to the story. There's not only is the C algebra case generalizing the matrix case, it's also generalizing the commutative case of the Hellinger distance. So, so maybe it should be called the Bures Hellinger distance now. I don't know, but maybe future papers or something. Okay, so some of the first results on it is just to prove that it is a metric. So Fahrenheit and Rahman did it in the unital case because that's again when they generalized this thing to the unital C algebra, and we verified it for the non-unital case here. Wait, again, it is actually non-trivial to check. It is a metric, but in the unital case, and we just verified that unitization does do the job for you in the non-unital case, which did take a little work too, but the main thing was the unital case in this situation. I want to give credit where it's due to Fahrenheit and Rahman for that. Okay, so other things that we checked, we have this topology in a subset of the C-star algebra. So one natural question is, well, how does it compare with the C-star norm? And one would hope that the topology is weaker, the Bures metric, because it's sort of built by this trace construction. And so we did verify that, in fact, it does give you weaker topology. Also, we found that if A is finite dimensional C-star algebra, then the topologies do coincide, in which case the topology is compact. So again, this is one of these situations where you can't quite use that it's a finite dimensional vector space because it's not. The density space is not. So there's some checking there. It's not just an immediate sort of result there. And in this case, because you're also compact, you do get uniform equivalence. You get the identity map is uniformly continuous for free because you're on a compact set. Okay, so we also in the paper, if you want to look through, we also had fun providing examples for which the topologies do not coincide in the infinite dimensional case, of course. So we worked through that as well. Yeah.
So if you're going to talk about metric space, you guess you have what you're looking metric on is the state space. So is it clear that this D sub tau lives in the state space?
It's not obvious. I'll show you later. Yeah. Oh, yeah. I'll present later. Yeah. 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 When we get to the yeah. No, but that's a good reminder. Yeah. Okay. Yeah. And so I kind of split up the thing into Bures metric first, and then the other half of the talk. Yeah. Oh, yeah. No. Yeah. No, I didn't. Yeah. Yeah. No. Yeah. You didn't miss anything. Yeah. We also did this sort of Heine-Borel theorem. What do I mean by a Heine-Borel theorem? I mean that we checked that the C algebra is infinite dimensional if and only if the topology on the density space induced by the Bures metric is not compact. And we also, yeah. So this one will present. So of course this is an equivalent statement, but I think it's nice to see an example. So here's an example of a case where you get, well, in fact, you get not totally bounded. But I also want to present this just to get an idea of, like, I mentioned this earlier about disjoint support and whatnot at maximum distance. And so that's all we're kind of capitalizing on here is we just needed to find enough things in this. So here we're looking at C0 natural numbers. And then we can put a standard faithful trace on it. Well, faithful state, which is trace because it's commutative, but I just like to keep using trace to remind us that is important to the story, even if, of course, not if commutative doesn't matter, but still it's important to remind yourself. Okay, so yeah, so basically you just have to find enough things of disjoint support that live in this space. So, and in fact, infinite countable set, right? So that's all we did here. So these are all in here, and then again, disjoint. So these are just characteristic functions of the singleton, and so you automatically get distance as 1 in the Bures metric. So therefore, you have something that doesn't even have a Cauchy subsequence. So it's not only just not compact, but it's not totally bounded, which is important for it, of course. Not really important, not maybe that important for topological considerations, but we're dealing with metric spaces. So yeah. But again, as we mentioned, as you saw before, any infinite dimensional C-star algebra with the faithful trace, the Bures metric will not be compact, but I think it's nice to show an example as well. Okay, so now we're moving on to the second half of the talk, where we talk about putting this metric on the density space coming from the quantum metric. First, we're going to talk about the unital case, and then the non-unital case. The unital case, as Otter mentions, compact quantum metric spaces. I'm going to skip this because it's basically the same thing he was saying. You're looking at a non-commutative. I'll go through a little, still mention a couple of things. You're looking at non-commutative sort of Lipschitz algebra in some sense, right? So we have a Lipschitz constant and whatnot. Here's this result due to Kantorovich, Otter mentioned. In the classical case, you get metrization of Weak-Star topology in the state space. And then here's a variation of the definition Otter gave. There was, and again, this is not even Riefel's original definition. He used order unit spaces, for example. So which the subordinate elements, you can also define things on the whole C-star algebra. But there's many variations. But this has the main things: dense domain, vanishes only on the scalars, and you get this metrization. Well, you require this metrization on the Weak-Star topology. But thankfully, Arielchan also mentioned this other. So here I'm now being careful to be on the Silverton elements. Just as we transition to other stuff, but this Ozawa and Riefel, this appeared in a paper of Ozawa and Riefel. We have this equivalence for the metrization of the state space, given this. And again, as I mentioned, this is basically just there to get rid of the scalars, right? Because if you don't have this condition, then scalars have Lipschitz lip norm less than or equal to 1, in particular 0, so therefore they're in this set. So, but yeah, this will be important for later. I highlight this because when we go to the non-unital case, you kind of don't want to rely on this metric to do things for you. So how do you want to define things in the non-unital case? It'll be more related to something like this, some condition related to these sort of totally bounded sets. So that's why. So keep this in mind. I'll remind us later, but this is why I'm mentioning this equivalence in particular. Some examples. Again, Otter mentioned this. You can get examples. So again, the spectral triples give you a candidate. Yeah, and I just mentioned some examples with Jens, the Polish spheres, and then this other paper just mentions further results where we show convergence of Polish spheres to the sphere. So Jens and I established that this gives you a quantum metric space, the Sankari spectral triple in this way. But then later, Jens and David and I show this convergence result. As I mentioned earlier, that's another big part of this quantum metric geometry world is this result about convergence of spaces. And again, just a reminder, these do not several time candidates, and they do not guarantee to provide a quantum metric. So just to really make that clear. The AF case that Otter was assuming to is here. Otter was alluding to, not assuming, alluding to is here. Again, this is motivated by work of Christensen and Ivan. We sort of tweaked their construction to get something that didn't involve equivalence constants, but their construction's just as interesting as well in its own way. But for our purposes, there were some equivalence constants in their construction that we just wanted to try to do away with. But also we answered similar questions recently back with the work of Christensen and Ivan. So anyway, but the idea here is, you have this filtration, but in this case, given by actual C-star subalgebras because you're AF, finite dimensional C-star subalgebras because you're AF. And yeah, basically you build the L semi-norm here is just seeing how far is controlling how far you are. So for example, if you're in the unit ball here, you're saying that you converge as the sequence E and tau of A converges as fast as with the speed rate of beta of n to A, right? Because if this is less than or equal to 1, then you get the multiplied by beta. And the condition is that beta is just a positive sequence converging to 0. reals. Also, again, the talk really isn't about these convergence of spaces result, but again, I like to remind us that that's also part of the story of quantum metric geometry. We all also this semi-norm is specifically basically tailored to get a result like this, where you have this. So this is one of these non-commutative analogs of the Gromov-Hausdorff distance. So you have this space, these spaces converging to this space. So sort of capturing this sort of categorical limit and then metric limit here. Okay. Other examples we focus on. So this is sort of an amplified or pointwise. I don't know the right term. But you can look at C, you can look at C of XA. So here's some quantum metrics on C of XA, where X is a compact metric space, XT is a compact metric space. And here you still do use a Lipschitz constant in one way, but you have to sort of compare, you have to sort of have this extra condition to control what's happening with the infinite dimensional space where the functions are valued. So this allows you, so you do this whole conditional excitation construction, but then you define it pointwise and you get a conditional excitation on the C of XAN and from the C of XA to the C of XAN. And this has a nice property that if you view this C of XA as a tensor product of C of X tensor A, then on elementary tensors, you get a product rule with this semi-norm here. So that was a nice sort of result here to sort of say this construction is natural in some sense. It gives you like the Lipschitz, the quantum metric structure times the norm of A plus again the quantum metric structure times the norm of the other element. Yeah, and this is also based on related to some work with Tristan as well. And we'll revisit this example. All these examples I'm presenting for, we'll see them come back later. Okay, so here's answer to Ray's question. So now how do we? So that was compact quantum metric spaces and some examples that we'll revisit later. But how do we put now given the density space? And not only do you have a C-star algebra anymore, well, we'll get to, this doesn't require a quantum metric at the moment. We can just do this anytime we have a faithful trace, which of course isn't always the case. But so let's say, so again, I'm still in the unital case, just reminding us the definition of the density space. With that, we can define a state by doing tau of AB. And again, remember, tau is a trace. So this is very important for this to get a state. Yeah, and so this gives you an injection from this density space into the state space. And and the important thing is that it's injective, and that's by faithfulness. So this is also showing you where faithfulness is coming into play. And as a reminder, I kind of alluded to this earlier. This map ends up being surjective if you look at the matrices. So this is where, again, the quantum information theory literature, they just interchange the word state with density matrix. So be careful with that with that information. Yeah, but this is and again, in general, I forget specific examples, but yeah, but in general, this is not surjective, just in the matrix case. Okay, does that answer? Yeah. Okay, and just anytime now, let's say you have a compact quantum metric space, so now you have this Monte-Kontorovich metric. You can just borrow the metric on here, and then now you have a metric on the density, a new metric on the density space to play with. So back to this example. So this is a reminder. So we had this example here. Here I'm looking in the unital case. So instead of looking C0 of n, I'm looking at C of the one point compactification of the natural numbers. So, and that just gives, we can do a similar construction here. And with that, the Bures metric we saw before, the same thing happens here in the non-unital or unital case here. We still get the distance between those are 1 because you have disjoint support of these elements. And again, so this is a sequence with no Cauchy subsequence. So this is a reminder now, just cast in the unital case here. But what happens now in this quantum metric case? So first, again, there's this extra piece of data. We don't just, it's not enough just to have a faithful trace. Now you need to have a L semi-norm to make this, to have a compact quantum metric space. So we're going to use the construction of Frederick and I from that I had a few slides ago. And to use that construction, you need to first call out an inductive sequence of finite dimensional spaces. Here, take the Cn to be functions that are eventually constant at n, which is a nice natural construction. And then using the same trace as before, you get that the distances between these same elements, these little characteristic functions on singletons, that are scaled to be in the density space. Now you get that this is actual Cauchy sequence, because again, the requirement of this beta is sequence converging to 0. Now we have to add a condition of decreasing, which is fine, but that technically is not needed before. But here, to get this nice equality here, it's nice to add. We as far as we know, we needed decreasing. At least we don't see a way around it. But yeah, so just to show you the different nature, the Bures metric, this was a sequence that had no Cauchy subsequence, but now with the quantum metric on the density space, we get one that has that is actually Cauchy. And later I'll mention that. So this sequence I'm not showing later. It's actually also just not convergent, but it is Cauchy, but it's still not convergent. So we also don't have a complete space, but that's fine. Yeah. So in particular, the quantum metric and Bures metric are not uniformly equivalent because they have a sequence which is Cauchy in one space, one metric, and is not Cauchy in the other. So the identity map cannot be uniformly continuous. Okay, so just as we did before, now let's look at what this metric, some properties of this metric. Again, it's a metric on the density space. There's also the C-star norm metric topology on there. So it is weaker, and again, one would hope these are just nice little checks. One would hope these sort of topologies are weaker because this comes from a topology on the space induced by the weak star topology. There's not a direct connection there, but again, philosophically these things should be weaker. Also, the finite dimensional case, everything agrees: Bures metric topology, C-star metric topology, and the quantum metric topology, and again, the uniformly equivalent, just because they also end up all being compact as well. So yeah, I do highlight this uniformly equivalent a lot because in the case of in the infinite dimensional case, we've only found things that are not uniformly equivalent. We have not yet found things that are not topologically equivalent. We haven't shown that topologies don't equal, for example. Like, we still are looking for that example. So if any of you have any ideas, talk to me later. So that's why I'm highlighting uniform, because like the best thing we were able to do in many cases is either uniformly equivalent or not uniformly equivalent. Yeah. Okay, so the non-unital case. Okay. Yes, cool. So it's until 450. Is that the usual amount? Yeah. Yeah. Okay. Oh, okay. Sure. Yeah. Okay. Thanks. Yeah, because this takes a minute. Okay. Now we want to do the non-unital notion. So this is due to Frederick here. This construction or this definition. So we were now given a non-unital C-star algebra. We want a notion of a quantum metric space. So one does sort of, the natural thing to do first is to look to the unitization to see if you can get some sort of initial idea of what kind of quote unquote should be happening. So for example, we use this notation for the unitization, UA, which Frederick also used in his paper. So if you ever look at his paper, like, at least that's the notation he uses. So look into unitization. Okay, there's a natural way to extend a semi-norm or norm, whatever, on A to the unitization that has the right kernel, right? So the idea is, okay, maybe the unitization, again, we're back in the unital C-star algebra case. Maybe we want this thing, when we unitize, to mirror the compact quantum metric space setting. So again, this is kind of the natural thing to start with. And so the first part of a definition of a quantum locally compact metric space is you start with something called the Lipschitz pair. So this is a non-unital C-star algebra. We say AL is a Lipschitz pair if L is a norm. So be careful now. L is a norm on the subadjoint elements. That has dense domain in the subadjoint elements. And when you extend it, when you do this, again, we'll use the same notation for L, the extension of L to the unitization as that. But when you extend it, the kernel is just the scalar multiples of the unit of the unitization. Okay, so that, okay, I think, that's nice enough. Again, we're just copying the unital case for now, right? Just finding a way to sort of translate things to unital case and copy some of those things down. Dense domain, vanishing on scalars, right? Scalars being the unitization scalars. Okay, what about the rest of the definition? So it's quite involved. The best way I thought to explain this is to start with an incorrect definition. So the definition will have the Lipschitz pair as part of it, but what about the rest? So I'm going to go through 3 examples that should be quantum locally compact metric spaces. And they are, but if we start with an incorrect definition, they won't be quantum locally compact metric spaces. So what is an incorrect definition? So the incorrect definition would be to continue going in this route of copying down the unital case. So meaning, so let's start with the Lipschitz pair again. That's okay when, for copying down the unital case with the unitization. But the wrong thing to do then would be it would be wrong to define a quantum locally compact metric space to be a Lipschitz pair such that the unitization with that L is a compact quantum metric space. And it seems a little weird because at first that would be your first guess. Oh, just keep going along this route. And so meaning the remaining piece of information is, define a Monge-Kotorovich metric on the state space of the unitization, and then require that metrizes the weak star topology. So that's what I mean by this. So and one would think that would be okay, like that makes sense. At least that would be someone's a natural first attempt. And I'm here to tell you that that is not what you want to do. And I try to defend that that's not what you want to do by giving you 3 examples of things we really would want to be quantum locally compact metric spaces. For example, the first couple examples are related to if I have, I'll just write big on here. I'm not going to write a lot, so I'll just. Yeah. The people on the Zoom still see?
Yeah.
Oh, okay. So here, if I have a locally compact metric space, right? So locally compact metric space, you would at least want the commutative case to be a quantum locally compact metric space, meaning equip it with the Lipschitz semi-norm still, which is a norm now on this space because it's quantum, it's locally. So be clear, we're assuming non-compact. We really want to just be in the locally compact setting. We want this thing to be a quantum locally compact metric space. And unfortunately, if you use this incorrect definition, meaning you just say, hey, require the unitization to be a compact quantum metric space, there are 2 examples I'm going to show where that doesn't happen. So the first example is kind of maybe the easier one to digest, but yeah. So assume we have R, the real line, with the discrete, equivalent to the discrete topology, so given by the discrete metric. This is a locally compact metric space, of course. Now the unitization is continuous functions on the 1-point compactification, right? And given any locally compact algebra space, the unitization of C0 of that space is the continuous functions on the 1-point compactification. So, but however, in this case, you have, because of that, you have that the unitization is not separable, right? Why is that a problem? Well, it turns out nobody's really written this down, but this is true. I can go through a quick proof if you want. If you have a compact quantum metric space, so CQMS, I'm using for a compact quantum metric space, it must be the case. So if you assume, the metrization, weak star topology and all those things on the state space, L vanishing at scalars only, you must have that the C-star algebra is separable, the unital C-star algebra. So therefore, this thing would not satisfy this definition, right? This would not be a C0 of R, the C0 of the 1-point compactification of R with any semi-norm would not be a compact quantum metric space. Because again, let alone the Lipschitz constant semi-norm, right? So this really shows that, we're in a bad situation. If we assume this is the definition, this would be a bad definition because this would not be in the realm of quantum locally compact metric spaces. So then you might say, well, this is maybe a silly example, right? Maybe in the definition of quantum locally compact metric spaces, maybe we just want to say, hey, let's only deal with separable C-star algebras. So maybe that would fix this issue, right? Maybe like if we add, which may be a natural condition. I mean, usually in this metric world, quantum metric world, you're usually dealing with separable C-star algebras. Okay, so, but unfortunately, here's an example of a separable case where it's something that should be a quantum locally compact metric space, but if you use this definition, then you would not get it. So here's the next example. So now look at R with the usual metric, D1. Again, the unitization is C of the 1-point compactification. That's just to remind you of that. However, one can find that with the associated Monge-Kotorovich metric, there exist 2 states that have infinite distance. And again, if you're using the unital case, that can happen, right? Because you have to be a compact metric space on the state space. So therefore, again, so this one's really maybe driving the point home. Like this for sure is an example that you would want to be a quantum Loki compact metric space, right? Like maybe the other one, like I said, the one before, okay, get rid of non-separable stuff. But here, this is separable. It's probably the main example one would want. But yeah. Okay, so you're probably convinced that this is a bad definition of a compact quantum Loki compact metric. Like this should not be the definition, the requiring the unitization to be compact quantum metric space. Sorry. But let me just show you one more for a good time. And also a non-commutative example, because we're non-commutative geometries. We need to see a non-commutative example. So consider the compact operators. So on an infinite dimensional separable Hilbert space like little L2, there exists, which of course is any separable infinite dimensional Hilbert space. So I'm just making you believe me for a moment. So believe me that in Frederick's paper where he introduced quantum Loki compact metric space, he did show the compact operators does have a very natural, I can even write it down later if you want, but believe me for now, it does have a very natural semi-norm for which you get a quantum Loki compact metric space structure. Again, I haven't defined it yet, but just believe me for now that, well, and maybe just for a moment, just believe me that like one would expect there was this, like in the first paper someone introduces, right? But that does happen. We do get that. And also I'm sort of sneaking in a third piece of information here, which will come later. So in fact, the definition of quantum Loki compact metric space kind of requires three pieces of information, not just the space and the norm, the semi-norm. It requires some sort of teasing that, like, oh, what's this other thing we're going to need? But we're going to need some other thing. Okay, however, this does not satisfy this incorrect definition. This thing. Why? Well, one can show, given La Tremonti's construction of this LK, that the domain is actually everything. So it's actually finite on the whole space, which again is dense, right? So that's okay, right? At first glance, that's okay, which is okay. Anyway. So also on the unitization, you get the domain is everything. However, with Katrina and Frederick, we showed that for any compact CQMS, compact quantum metric space, the dimension is infinite if and only if the domain is not everything. So again, if we assume this structure was a compact quantum metric space, we'd have a contradiction here because the compact operators are infinite dimensional. So just again, really drive the point home that this is everyone agree this is a terrible definition of a quantum Loki? So now you're like, oh, what is the right definition? We really need to know the right definition. So let's go to that now. But I don't know, I think this helped me with learning this stuff, was thinking through this idea of like, okay, why not use this as the definition? So I like to present that when I talk about the non-unital case. Okay, so what is the correct definition? Well, let's go back to, again, the compact quantum metric space setting, because there should be still something there that gives us the right idea. Even though we can't copy paste it in the unitization to get the job done, maybe there's enough structure there that is good enough. And I'm being a bit informal here and maybe too philosophical, but the idea here is that, so recall that one of the definitions of a compact quantum, one of the equivalent definitions is that this space is, I know I said totally bounded before, compactness is fine because lower semi-continuity, but it helps to write this saying compact now. Is that this very special set, there exists a state, so which this set is compact, right? So the idea then is, okay, maybe we want, for the quantum locally compact setting, maybe we should just follow the classical idea of like, what is a locally compact space? It's a space that has enough compact sets, right? It's not compact itself, well, if you're considering a non-compact situation, but it's not compact itself, but it has enough compact sets. So maybe we can just find enough of these or things like these to be compact or totally bounded, and that should be our definition of a quantum locally compact metric space. So that is what ends up happening. So here, what I mean by enough of these, I mean cut downs, and we'll see what I mean in a second. The idea is that the approximate identity is now going to come into play. It's going to allow us to sort of approximate these totally bounded sets in some sense and sort of give us enough things. So, and so this is a nice setting where like, I like that you use both the unitization and the approximate and an approximate identity. So when we capture the data of an approximate identity, we require a little bit more information. So now we're saying ALM is a Lipschitz triple. So again, AL was a Lipschitz pair, which again just had dense domain and vanishing only on scalars in the unitization. of the semi-norm. And now we assume not just that we have an approximate identity, we want actually to find a commutative subalgebra of A that contains an approximate identity for A, not just M. So for like cases like, what would you take in certain cases? Of course, if you have C0 of X, take M to be C0 of X, because it's a commutative subalgebra that takes that has an approximate identity for the whole space. But just to give you something that's not just the whole space and the compact operators, you can take M. So there's no canonical choice of M. So I don't want to be. I know this slide is a little misleading, and there's not necessarily a canonical choice for M. But here's what people have done before. For here, you take M to be the compact diagonal operators to be your. That has an approximate identity with the projections, finite rank, standard finite rank projections, and then, yeah, and you then you get the whole compact diagonal operators from those. Okay. All right, so now this is an approximate identity. It's going to help us sort of like cut things down. So here's what I mean. So now here's finally the definition. And this is just a theorem definition. So I should say, like, I know I've spent a lot of time on quantum fluky compact metric spaces, but trust me, this is my best attempt at shrinking the work, because the definition itself is pages and pages. So but later on, Frederick shows, and it deals with the notion of the Brutian tight sets and tame sets. Very interesting stuff. Stuff that I don't have all in my mind because it's so intense and long. But here we at least get this thing that's this equivalent formulation. At least sort of captures this philosophy of you're getting enough quote unquote compact sets. So first, you start with the Lipschitz triple, and you assume there's a state and a compact set living in the Gelfand spectrum of M, our commutative subalgebra that contains a approximate entity, such that mu at the characteristic function is equal to 1. Of course, here what we mean is that, so mu is a state on A, so it restricts to a state on C0 of M. Well, we can think of C0 of the spectrum of M. And where does the state come from in the C0 case? The state comes from integration. So then we can make sense of integrating a characteristic function with the Borel set, right? So so even though, again, chi sub k doesn't live in C0 of M, it might not even live in A, right? We can still formalize what we mean by the measure or the integration of a characteristic function when the set that it's characterizing is a Borel set, in fact, the compact set in this case. So I want to be clear, like well, first the term Frederick uses to define these are local states. And one way to think or get an idea of these are they're highly non-faithful states, because the idea is you're requiring sort of measure 1 on a compact set. So for example, any point mass. And any point mass will be in here, because you can take the compact set of a singleton, right? Well, you can take a singleton to be your compact set. So, and again, point masses are highly non-faithful states. And the idea is to sort of, what's going on behind the scenes here is that you kind of want to, when you do this, these help you get rid of the approximate identity. So remember, like the purpose of this in the compact case, in the unital case, so forget the F and G at the moment, but the purpose of the set is to get rid of the identity, right? To get rid of scalar multiple identity. Here, these local states are going to kind of get rid of at least a tail of an approximate identity. It's going to get enough of that to sort of hopefully get things that are totally bounded. And then here, you can't hope for, in general, for this set to be compact here without the F and G, but you can take cut downs and require that. So this is, yeah. So again, really informally, this allows you to get enough compact sets to get you a quantum locally compact metric space. And this condition here, informally, this condition 1 is let's sort of get rid of the approximate identity, right? And not just the identity, because of course, extending this to the unitization does get rid of the approximate identity, the units in the approximate identity, but you also kind of want to kill off given an approximate identity, you want to kill off enough of that. And if you think of the point mass, that's a good concrete way to see that. It's a fun exercise.
What is the unit part?
So I should say, maybe I wrote it sort of as a definition instead. So this would be a Lipschitz triple. So given a Lipschitz triple, it's a quantum locally compact metric space if and only if the two following hold. Yes, yeah. Oh, yeah. It deals with it does deal with a non-unital metric directly, which again, that thing is just so much nastier in the non-unital. It's not even a locally compact space it's not even locally compact space in the non-unital case, like in the weak sort topology. So yeah, but that's where, but you do have to. So it's nice in Frederick's paper with the original definition. He does take care of like what to do with the non-derivative metric, and that's the original definition. And this is the definition where we get away from that and then just are dealing with the space itself. Except, I mean, here's a state, but still, yeah. Oh yeah. Thanks for asking. Yeah. So, okay. All right. So, so we can still. So now we have the right notion of a quantum locally compact metric space. The correct definition, finally. And yeah, we can do the same. But what if I also have a faithful trace on my C3 algebra? My non-unital C3 algebra in this case, we can still get this. This map is still an injection. It's quick to check. You still get an injective map into the non-unital metric, so you get something. So here's what I mean by just saying something. This is a wall of text, but let me just say what happens. Remember in the example, the C0 of R example with the discrete, with the usual metric, right? You get distance infinity between certain states. So therefore, at face value here, this thing could take value infinity. And in fact, I don't see why it couldn't. Like there should be some situations where this can be infinite value on here. And again, we would at least, we in the non-cubic metric geometry world, we do deal with things with, even the semi-norm, right? The L semi-norm can take value infinity. So like that's not the end of the world, right? To have a metric that takes value infinity. However, again, the underlying philosophy of all this, or the idea of this project is to compare with the Bures metric, which is a bounded metric, right? Not just finite between any pair of states, but it's also a bounded metric. So this is kind of not what we want for our current work. We don't want something that can take value infinity. So we want sort of a subclass of quantum locally compact metric spaces to talk about, for which you automatically get a bounded metric with the Mondrian-Trovic metric. And what subclass of quantum locally compact metric spaces do we want? I'm laughing because we want the wrong definition to be. So that's why I spend so much time on the incorrect definition, is that we use it later. We are going to use it now. So it is a nice. It should not be the definition of a quantum locally compact metric space, but as a subclass of quantum locally compact metric, it's exactly what we want, or at least a nice class for what we want. So, and of course, we don't call it a quantum locally compact metric space. We give it the name quantum Lipschitz triple, and it's the definition if, in fact, you do get with the unitization, you are a compact quantum metric space. So all those three examples I showed do not satisfy this, but they are definitely nice and important examples we'll mention in a minute, for which you are a quantum Lipschitz triple. So it is a non-empty set. There are actual quantum Lipschitz triples that exist that are nice. We did first check that if you have a quantum Lipschitz triple, you do get a quantum locally compact metric space. Like, yeah, okay. And it basically uses that. It also uses that theorem definition that I displayed. That's why I displayed it as well. It's pretty quick just using that definition to prove this fact here. So what satisfies this wrong definition, or what are some examples? So basically, this is just a sort of extended version of just it's better if I just have it on the slide. There you go. So here are examples. So again, if you use R, like R, the locally compact metric space, R with the usual metric, that's not going to work. That's going to give you a quantum locally compact metric space. Like we found the right definition to get that. It won't give you a quantum Lipschitz triple though, but if you have situations like this, if I have like the half open interval, the one compactification is this with the usual metric. So these settings, you do get the situation where the unitization now automatically is going to give you a compact quantum metric space. Or you can, another example, N, one compactification, you could put this metric as well. So basically, this is just saying that C0 of X, where X is something like this, you do get a quantum Lipschitz triple and also a quantum locally compact metric space. But you can also, you don't need just C0 of X, you can have values in an AF algebra using this trick before that I mentioned, with sort of this Lipschitz constant plus this piece that takes care of the infinite dimensional nature of the AF algebra. yeah, so there are many examples, nice examples that do give us the wrong definition or quantum Lipschitz triples, which still satisfy what it means to be a quantum locally compact metric space. Yeah, so we do check next that if you have a quantum Lipschitz triple, you not only get a metric now on the density space via that injection, you do also get a totally bounded metric, not just bounded, but totally bounded. Yeah, and I'll be wrapping it up right now. And we also checked that the topology is weaker than the C-star non. We know these standard things to check. And then what happened next was that's kind of as far as we can go with general results, because with the quantum metric, you just have so much more variation with the L semi-norm that doesn't seem we can get general results, but at least we can get some families of examples. So here we just looked at matrix valued functions on the quantized interval. This is very much related to the C0 example, so that's why I mentioned those examples before. And here you can take this again, this state here, and just amplify it to the this is just a tensor product of the trace and the omega, right? So well, 1 over n, the trace. Yeah, and in this example, we can also, so the reason we wanted to look at this example specifically is that this example, what we do is we view this thing as an AF algebra, right? Not just this, I mean, finite dimensional, this is an AF algebra, but this whole thing is an AF algebra. And then we used the quantum metrics from Frederick and I on it. So I'm pointing that out because this quantum metric has nothing to do with any metric on n. So, and why is that important? Is that this isn't just like relying on classical things. Like, yes, this is C0, C of something. I mean, yes, and evaluated in a non-commutative space, the matrices. But we want to do an example that didn't just rely on like some classical standard, like Lipschitz constant tricks. So this is the one we want to look at just to provide us a weird example, a weird family that's sort of purely quantum metric in some sense. It's not related to the classical case directly. Yeah, and in this case, we get that the Bures metric and quantum metric are not uniformly equivalent. Again, we have no example right now at the moment of non-topologically equivalent. We still don't know about that, but at least we get this. And then also, remember, we had this Heine-Borel theorem for the Bures metric. Again, we have no hope at this moment to get a Heine-Borel theorem for the quantum metric, but at least in this case, well, I'll show the result here. We do get the quantum metric on this infinite dimensional non-unital space. Of course, non-unital implies infinite dimensional, but I just want to highlight the infinite dimensional part. We get that it's not compact. So again, maybe no hope of getting a general Heine-Borel theorem, but this, and I mentioned this theorem before because this was also a nice result. In this case, we get that convergence in the quantum metric implies pointwise convergence, and I thought that was a nice sort of way to, it was just a nice comparison to see like, okay, at least like, so it's like weaker than the C-star topology, but it's somehow stronger than the pointwise convergence. So it somehow lives in this strange middle ground in a cool way. Yeah, but yeah, that's all we have. Yeah, thanks for your attention.
So thank you very much. Do we have questions from the audience? Person.
So saying that there are two different metrics, they're not uniformly equivalent. You had this example with what, like just C0 of n, I think, and
yeah, I'm here. Yeah.
So it was yeah. So okay. So you had a slide even when you had like a sequence which is Cauchy one but not Cauchy.
So that same sequence, we just amplified it to get the sequence for here. Yeah, the sequence was just yeah, this is an is 2 to the n.
Right.
That's the characters. Is that what you're?
Yep, and that's
so Bures metric you get just because they have disjoint support, you get
it's just
distance one and then
uniformly discrete, and then and
then here in the quantum metric you get so when you amplify to the matrix case you get less than or equal to 2 times. You just get a less than or equal to, but then you still get Cauchy, right? Yeah.
Okay, here's this Cauchy conversion. It's Cauchy. Okay, so yeah. All right.
The seesaw norm is stronger for both, but we don't know directly in the infinite dimensional. Again, finite dimensional, all things are the same, but infinite dimensional, yeah, we don't even have that. So a lot of fun to be had. Yeah.
And then can I ask us to, first of all, just in case it
Okay.
is there? Well, I guess I'm the chairman, no? Yeah, Tishan, go.
Yeah, thanks, Ray. So my question is it easy to describe these two measures on these two states on C0R, whose Monte
yes. Yeah, again, yeah. So we actually have that in the paper too. I'm not saying I'm not trying to be rude and say just look at the paper. I'll mention now. Just so I have the results so everyone else is. There we go. Okay. So, for example, take nu to be, let's say, the point mass at 0. And then mu, what we do is we take a function, it's like, one of those like at functions. So h of x, I think remember directly, it's h of x is equal to 1 over pi times 1 over x squared plus 1. Something like this. So, and then we integrate against that function. And then the measure, that state from integration against the induced by the Lebesgue measure and that function, where when you integrate a function, you just multiply by that function, the distance between that and the point mass at 0 is infinite. And the idea is you find a sequence of functions that are just growing with slope 1, because we have to take care of the slope. When we measure the modular metric, make sure and you just start at 0, like everything's 0 up to 0, and then at 0 just take a sequence where you just keep growing, and it works out. The nice. I think the h of x function was just like we didn't need that one particularly, but I think you can probably take. It's just these functions that are kind of like the beginning of an approximate identity. Like it's like the first step of an approximate identity. Yeah. But does that help? Does that mean? Yeah.
Yeah. Yes. Thank you very much. And thanks for the very nice talk. And I'm sorry I could not be there in person.
No, and I want to say Jack Spielberg says hi. Anyway, he's like,
okay.
He's trying to say hi. I was like, yeah, but anyway, but sorry, I'm satisfied with that. Yeah, cool. Yeah.
Cool. Thanks.
Yeah.
Okay. Are there more online questions? Just unmute yourself. In that case, then I have a question. So is it clear, maybe I missed it or got confused, that if you have a compact quantum metric space, then you will have a locally compact quantum metric space?
Yes. Yeah. So and there's also, so this is kind of, so there is so there's a quantum metric triple. If the unitization is a compact quantum metric space, then yes, you get this. I should mention that what Frederick does in this paper, this 2012 paper, where he introduces quantum locally compact metric spaces, he actually does say, a lot of his definitions don't require to be non-unital, right? So it allows you to be unital still. So he does check later that if you have a compact quantum metric space satisfying the definition of a quantum locally compact metric space. Sorry. If you have a compact quantum metric space and you pretend it's a non-unital space, then it does satisfy being a quantum locally compact metric space, which is a little different. It's a little different than this. Yeah.
So then in this case, if you were to go back to like what you guys did for Padlesh.
Oh, yeah.
Would it be easier to, so it's a weaker condition. So is it easier to prove? In this example, would it be easier to prove that it's locally compact?
Did you mean that condition Jens had with the...
No, just the actual, for the single example of Padlesh. If you were to try to write the paper again, but this time you wanted it for the weaker condition of locally compact, would that make things easier or be just as complicated? Sorry, I'm asking you about a paper from 6.
So but I guess so here. I guess maybe I'm just misunderstanding. So the polar spheres are unital, though, right? Yeah.
They're unital, but verifying that they're a compact quantum metric space is non-trivial.
That's true. Yeah. They are. Yeah, they are. That's a good point. Yeah, they are unitizations of the compact operators. Yeah. So I think I think it would be like equivalent. No, their approach would be the same, I think.
So it would not be easier, basically.
Yeah. I think it would not be, yeah.
Yeah, because I was just
yeah,
like,
thanks for the reminder, Karen. Yeah.
after CP1, after Podlish, you get CPN, and then we tried to go with the ends to the Grassmannians, and the approach just went out of control.
Oh, okay, yeah. Yeah. So I don't think it would be easier, yeah, to use this.
Yeah, but exactly. Yeah, I mean, if it's not easier for Podlish, then it's not going to be easier for them. So that was just my naive. We could verify this weaker condition, but it's probably going to.
Yeah, it's always good to have hope. Yeah. But sorry to crush the hope.
So a more an obvious question is like, what about convergence, metric convergence in the locally compact cases? That
thanks for mentioning that. So Frederick just introduced in December 2025, so hot off the presses, a quantum Gromov-Hausdorff distance, well, propinquity for the non-unital case. So yeah, interesting enough, in that case, you don't get a metric like Riefel's quantum distance or even Frederick's propinquity. You get everything triangle inequality. You get some sort of constants against the triangle, like distance between x, y is actually equal to some constant times just between xe and some other constant. But it's enough to give you a nice topology still, and still talk about convergence results. So it's called, I think, an inframetric. It's when you have these sort of constants sitting next to the right hand side of the triangle inequality. Yeah. But yeah, no, it's very nice, and I'm very excited for that. I've been waiting years for him to finally, not that much. Anyway, yeah, I'm very happy about that. Yeah.
So thank you. Do we have more questions, Karen?
These constructions of yours were for like a single faithful trace. But of course, for example, like AF algebras can have many faithful traces.
Yeah.
Have you looked at how they might different? Are they equivalent?
No, I don't think we thought about like different quantum metrics, but yeah, no, maybe, yeah, that'd be interesting. Yeah, cool. Thank you. I don't know right now the into it. Yeah, I know there is something that for the varying changing out like doing dtau L for fixed tau and different L's. I think that would basically rely on one of Frederick's results from a while ago that, and this actually might go back to the question Tristan had for Ade. Like if you have fix a dense subalgebra, I don't know any way of creating a seminorm for that, but if you have two seminorms for which that subalgebra is their domain, they have to be a norm equivalent. Yeah, like equivalent, semi-norm equivalent. Yeah. So meaning like equivalent of the really strong sense. You have constants alpha, beta. So I think that's where it would boil down to if you replaced L with some other thing. But I don't know about the trace. That's interesting. Yeah. Thanks for the question. Yeah.
Okay, so no more questions. Then in that case, we'll thank Konrad again.
Yeah, thank you. Yeah.
And next week's talk is Fabio Gavarini from Tor Vergata, who will speak about quantum. Big news. Okay, that's fantastic. Because I thought Fabio was next week. Brilliant. Okay. Yeah, I got this part from the recording. Yeah. Okay, next week you can just slip. There's San Shan Hua from the University of Munster, who will speak about Cartan subalgebras of self-similar graph Caesar algebras.